Thank you. So this talk is going to be, at least to my taste, a lot more pedestrian than many of the talks we've heard in the last few days. So I hope it will also be a little bit more relaxing. And as is my custom, the important people's names are in bold, which is to say the young people who have done a lot of the hard work on various, actually there's kind of multiple projects I'm going to talk about. And some of them are on the job market this year, so keep your eye out for them. Now, it gives me great pleasure to thank the organizers for the opportunity to be back here at the GGI and in another fun physics workshop, and gave me the, well, is this cooperating? No, it's not cooperating. All right, well, we'll do it manually. What is going on here? There we go. So because as I now realize, it was actually one of the early workshops, had the opportunity, I think this was my first workshop at the GGI about 17 years ago. And that workshop played an important role in the creation of Black Hat, which was one of the things that helped popularize the field of scattering amplitude. So it's really great to be back here. I've had the opportunity to be back here in the intervening time as well. But so I think for most of the audience, there's really nothing more that needs to be said to present Feynman integrals than the pictures and the symbol. But in order to introduce notation, I will actually write out a multi-loop integral. Let's see here, I guess I should actually focus on this screen. So the key thing we're really going to be focused on here is the numerators, which are polynomials in the loop momentum. Everything else is pretty standard. And just to remove the clutter, I've removed the 2 pi's. So if you're worried about the appearance of those. So as most people know, there are a lot of linear algebraic relations between different Feynman integrals that you can find by the very developed method of integration by parts, essentially adding and subtracting total derivatives. And that ultimately allows us to choose a basis of master integrals. And the question is, which ones should we choose? So the vision here, or the motivation, let's say, is to be able to select Feynman integrals for the basis based on their degree of divergence. And the hope is that if you organize things in that way, you'll lead to a simpler and more transparent representation. And at the very end, I'll kind of give you an appetizer, what I hope will be an example of that for future work. But at the moment, the first step is to classify and organize systematically all the integrals that have the lowest degree of divergence, which is to say the finite integrals. Actually, as part of this project, I won't really spend much time on it today. There's integrals which are of interest, which have even lower degree of divergence, namely integrals which are what I call evanescent, so that they vanish as the dimensional regulator epsilon goes to 0. And this subject has been studied in, I think, a little bit less systematic a way and with very different ideas by many people, and I've just listed some of the collaborations here. So I'm mostly going to gloss over the fine print. What exactly you mean by finite is not as simple a question as it might seem. And we're going to focus for the most part on what I'm going to call locally IR finite integrals. These are integrals which you could do strictly in 4 dimensions. There's other ways of getting finite integrals. And also we're going to impose what I call strong UV convergence, so that the integrals are UV convergent by very strict power counting. And that again is something that you can relax. So let's go back and look at a very simple example, which everyone kind of knows. And just to set the stage, which is at one loop. So the canonical basis, not exactly the basis that would come out of differential equations or IBPs, is that of a box, a triangle, and a bubble. And the box and the triangle integrals both have 1 over epsilon squared divergences, which are IR, and the bubble has a 1 over epsilon divergence, which is basically a UV divergence. So what can we do? We can trade the 4-dimensional box, which has the 1 over epsilon squared from the collision of soft and collinear divergences, for a 6-dimensional box, which is finite. And that's a standard kind of decomposition equation where the C's here are coefficients in terms of the external Mandelstam invariance. And when you do that, you get a spray of triangles. And so now you have all the IR divergences are isolated in triangles. And so the kind of idea here is to try and generalize that to higher loops. So again, here I've used a P rather than an N, but it's the same object, polynomial in the loop momentum that we're inserting. And something that will be very useful to us, I'm sure familiar to many people, is our Graham determinants. So these are determinants given in terms of 2 sequences of momenta. And because of the determinantal structure, then whenever 2 momenta in the same row become collinear, if they're massless momenta, then this Graham determinant will vanish. And that will be kind of a key building block that will let us express the finite integrals in a nice form. So for example, at one loop, you can build this Graham determinant with the loop momentum and the 3 independent external momenta. So this integral, you put this Graham inside the numerator, it's finite, and in fact, it turns out to be proportional to the 6-dimensional box. Now, we can do a similar thing for the pentagon. We can decompose the 4-dimensional pentagon, which again has 1 over epsilon squared singularities, into a 6-dimensional pentagon and a set of boxes. The boxes carry the singularities, and the 6-dimensional pentagon is finite. But in fact, here the coefficient turns out to be order epsilon. So in fact, if we're only interested in the amplitude to order epsilon to the 0, so this is not part of a building block of some higher loop computation, then we can truncate and we actually get a free extra relation, which is not given by integration by parts, and it's something which we call an evanescent relation. But again, I'm not going to really focus on that very much. And again, this can be generated by a Graham determinant. Now, again, the 4 independent external momenta and the loop momentum, and this one can kind of straightforwardly see by construction is going to be of order epsilon. So we'd like to generalize these ideas to higher loops, and we should look again at one loop at how the IR singularities arise, and that's something that we'll generalize, and the analysis of them can generalize. So these arise from regions, of course, where denominators vanish. But if you have a single denominator vanishing, then that thing is integrable. If you have 2 denominators vanishing in an invariant independent way, then you get a 1 over epsilon singularity. And if you have 3 denominators vanishing in an invariant independent way, then you get a 1 over epsilon squared singularity. I'm sorry? So that the presence of the singularity is not dependent on the values of the external invariants or the external momenta, because of course there's another class of singularities which is very interesting, which is the point locations of the branch points, which are precisely the ones that are dependent on the invariants. But that's not what I'm interested in today. So generically, the 2 denominators that are vanishing for 1 over epsilon have to be adjacent propagators separated by a massless leg. So for example, if you have a leg corresponding to the difference between 2 momenta inside denominators, then they have to be massless. And then it's when the loop momentum is collinear with those that you get a so getting on shell and collinear with that difference, that you get a singularity. And similarly, 3 denominators vanishing are going to be from adjacent propagators that are separated by a pair of massless legs. And it's when the middle momentum is soft, and then you both get the collinear conditions for the 2 massless legs, and you get an additional soft singularity from the massless middle propagator. So the idea is that, of course, in planar integrals, generically, the singularities are all logarithmic. It's not true in the non-planar case, but everything I'm talking about doesn't really care so much about that. And so the idea is that if you have even a fractional power of the singular quantity in the numerator, that's enough to cancel off the singularity and give you something which is integrable in 4 dimensions, certainly analytically, and perhaps with a little bit of care to the numerics, even integrable numerically in 4 dimensions. So the first thing, this is actually a paper that came out, or the preprint came out last fall, and we've been fighting with the referee ever since. So even after decades as a physicist, it's hard for me to predict which papers will run into trouble with referees and which will sail through with absolutely no objections. In any event, this is something where you can really derive everything step by step, and you proceed topology by topology. This is not going to be the focus of the talk, so I'm really just going to go over this in quickly. But the basic idea is you solve the Landau equations in a mixed representation. There's 2 of these. There's linear and quadratic equations, and there can be subtleties for non-planar integrals because of the question of potential singularities inside the region of integration. But let's not worry about that. Each solution of the Landau equations is a singular surface. It's a place where singularities can occur. And we go ahead and classify the degree of divergence following ideas outlined by Babis Anastasiou and George Sturman, which in turn is based on much older work of Sturman and collaborators. And so you're basically building a scaling invariants that approach the singular surfaces, and then you're asking what's the degree of divergence as you approach the singular surface. And so now you go to build finite numerators. You start, let's say, at 2 loops with all the different factors that you can build up, and then you build numerators of some fixed degree in the loop momentum. And I'll sometimes be using the word rank, which we've appropriated to talk really about the degree of the polynomial. There's no free indices in anything I'm talking about. And we apply general coefficients, and then we require that every singular object have a vanishing coefficient. And in the planar case, that really is just going to mean 1 equation for each singular surface. In the non-planar case, because there can be deeper than logarithmic singularities, there may be multiple equations for every singular surface. Anyway, we can solve those equations, and then we end up with some number of independent numerators. And so these numbers are cumulative. They include all the lower degree ones. And so this is the maximum order in the loop momentum. This is at for the planar double box. There's nothing of degree 1. There's 2 of degree 2, 18, 89, 247. These are not particularly obvious numbers, nor is this particularly a manageable way to think about the problem. Because if you ignore the UV for a second, then, and suppose you have some finite numerator, well, you can multiply IR finite numerator. You can multiply by any polynomial in the loop momentum, and you get another finite numerator. So the correct way to think about this is, at least before you're talking about UV power counting, is that of an ideal. And so rather than enumerating all the polynomials in the ideal, you want to ultimately find a basis. I don't know of any good term in the mathematical literature for the object that's left after you impose a certain power counting. And so we've adopted the language of a truncated ideal, which may or may not horrify mathematicians, but hey, we're physicists, so I don't worry about that. So I think probably in this audience, there's a fair fraction who know about ideals and how to manipulate them. Why don't we have a show of hands? Who already knows all about ideals and how, well, maybe it's almost everyone. So you can go to sleep for the next few minutes. Anyway, for the benefit of those who don't, I thought that we should have a foreign language lesson. Now, actually, for this particular language, I'm not the right person to give the lesson. And the main lesson here is actually you shouldn't learn about animal behavior from Duolingo. To each app its own expertise. And I may not even be the right person to give the foreign language lesson about ideals, but I'll just do a very quick overview. So the idea here is that, or at least the original motivation is we want to be studying systems of polynomial equations in some multiple variables. And we have some number of basis polynomials. These are ultimately the things that we want to find. And we can build other polynomials out of them, just as in the case of the numerators, by multiplying by other polynomials in these same variables, and that gives us the ideal. And these are all functions which vanish when all of the generators vanish. So what we want, in some sense, is to be able to find the simplest set of polynomials that generate the ideal. We want to know for a given numerator, is it in the ideal? Is it not in the ideal? We would like to maybe be able to subtract out the part that is in the ideal and have the part that's left over in some independent canonical way. And basically, to answer these questions, first of all, in multivariate analysis, one has to choose an ordering of the monomials. That's where things are. Otherwise, there's no canonical way to do it. And then you build what's called a Gröbner basis, which is a special set of generators that allows us to answer these questions. Now, are there any graduate students here? Yes, there's a couple. So it's always the thing I like to point out that Gröbner was not actually the person who invented Gröbner bases. They were invented by a guy named Buchberger, who was Gröbner's graduate student. And so he named it in honor of his thesis advisor. So I think that's always something that the students should keep in mind. There's straightforward and much more sophisticated algorithms for building these Gröbner bases from a set of input polynomials. And there are a number of open source, well, not open source, but at least freely available packages that allow you to construct these and use them. And the basic point is that it makes the polynomial division independent of the order in which you divide by polynomials. It's otherwise not true in multivariate case. And it gives us a set of equations or a set of polynomials that are equivalent to the original set that we started with. And I think that's actually all that we really care about here. So we're going to apply this technology of Gröbner bases, and there are different ways of doing it. You could compute them all at once, or you could proceed degree by degree. And in any event, when you do that, then you find a much simpler picture. And in a sense, for the double box, all of the independent IR finite, and then after truncations, all of the independent finite numerators are generated just by 10 different polynomials. And you'll see, for example, there's actually nothing new at degree 5. It's all built out of lower degree polynomials. And you can give these things a nice form, essentially using, if you like, Van Erven-Vermazerin basis, or equivalently, again, building out vectors out of Graham determinants, and then building objects that are kind of designed to probe the epsilon directions using two loop momenta. And when we do that, then, for example, for the planar double box, then the order 2 finite numerators have this very nice form. They're either gram determinants or products of gram determinants. And one can write down the rank 2, 3, and 4, and you'll actually see that the rank 4, of course, you could take linear combinations of these to obscure it, but in fact, they're all reduced integrals. They're all really daughter integrals. So the number that are strictly of the original topology is in fact even smaller. And with this basis, we can write down an all-loop ladder conjecture. And again, the key point is that for the independent finite integrals, the kind of the basis elements stop again at degree 4 for this class of topologies. And we've checked this through 4 loops, and it does in fact check out. So I've taken a little bit longer to do the introduction than I wanted to. So, okay, this is straightforward and it's hard work. You have to write some code and debug it and all that. But sometimes, as the cartoon would suggest, we just like to go out and explore. And so that's really what I'm going to be talking about the rest of the time, an independent strategy. So that's an analytic strategy, if you like. And here I want to talk about a geometric strategy, which has some overlap with things that we've heard from previous speakers, because it has some connection to tropical geometry. So this is not something which at least I know how to derive from first principles yet. There's a lot of conjectures that we stick in along the way. And here, the hard work is going to be done in the parametric representation, even if ultimately we're still going to be building results in the loop momentum representation. And our focus here, so imagine that we have some monomial in Feynman or Schwinger parameters, and of course they have different exponents. And our focus will really be on the geometry of these exponents and these exponent vectors. So that's really going to be the thing. And this builds on a theorem of Berkesh, Forsgård, and Passere on the convergence of Euler-Mellin integrals, which you can think in the parametric representation of Feynman integrals as a special class of them. So we take all the exponent vectors that appear in our problem, and those give us lattice points, and we can now build the convex hull. There's a precise mathematical definition of it, but you can imagine that it's this kind of smallest convex object that wraps those vectors. That's kind of a physicist's definition. You can also give what's called an H representation, which is that it's a region in higher dimensional space. The dimension of the space depends on the number of Feynman parameters. It's a region bounded by some set of inequalities. And there is a connection to tropical geometry in that the facets of this polytope, I guess the normals to the facets are related to things that you study in the tropical geometry. So if in the generic case we have 2 non-trivial Szymanczyk polynomials and they appear in the denominator, so we put them in the numerator, and then we're supposed to look at the Newton polytope of this particular a product of powers of the Szymanczyk polynomials. And here we're going to take, for this purpose, we're going to take D to be 4, and everything else is an integer. And so these things are actually integer exponents, so these are polynomials. So there's a certain Newton polytope that's associated with that. You look at all you multiply it out, you look at all the exponent vectors, and then you build the convex hull. So you can re-express this as what's known as a weighted Minkowski sum, and yes, that is the same Hermann Minkowski that we know and love for other reasons. And what BFP tell us is that if we have if we now consider not just the basic Feynman integral, the scalar Feynman integral built with U and F, but we look at the integral of a certain Feynman parameter monomial that's now put in the numerator, that there are certain technical conditions on U and F. They're not supposed to have zeros on the faces of the polytope, and this is generically true for planar integrals where you have a Euclidean region. It may or may not be true for non-planar integrals. And then you're supposed to find something that's called the relative interior of the polytope. And when the polytope is really full dimensional, then it's kind of really just talking about the interior. And there are specialized packages. Leonardo de la Cruz is really the expert on this subject in our little collaboration, likes a tool called nConvex. And, but that's actually very heavy duty. All these problems are quite, I don't know if they're P equals NP type problems, but they're difficult problems. So it's nice to have conjectures and shortcuts. And one of them is a conjecture that we have on the generating function. You can build a generating function, and then you look at a certain manipulation on the generating function, and that tells you what the relative interior is. And but however you find that relative interior, if you another conjecture is that you can actually take your numerator polynomial in the loop momenta, you convert it to Feynman parameters, and now you look monomial by monomial independently at each of these Feynman parameter monomials. And if each one of them is in the relative interior, then the integral is finite. And if that condition does not hold, if there's one of them that's not in the relative interior, then the integral is not going to be finite. Again, this is a conjecture. Yes. I'm talking about the numerator. Yeah. So the polytope is built out of the semantic polynomials, and now we're adding these extra ingredients, the numerators that are whose origin is in the numerators that the non-trivial numerators that we put into the original Feynman. So how does this? So let's look at a very simple example. It looks much more complicated in this language than what you know, but that's, I think, just because everyone is less familiar. So let's look at the massless box. So, there's U and F. And unlike the usual choice of delta functions, we're going to use the projective invariance to ultimately set the last Feynman parameter to 1, and then these integrals run from 0 to infinity, so U remains non-trivial. So the first thing is that actually these polytopes contain a huge number of lattice points that can never arise from an actual Feynman integral. And so the first simplification is you ignore all the points that can't arise from a Feynman integral, and you have, let's say in this case, you have these exponent vectors that are inside the polytope, and then you run your relative interior algorithm, and you find that there's actually just 2 points at rank 2 inside in the relative interior. And of course, we've for the simpler cases where nConvex kind of completes in a reasonable amount of time, we compare the generating function conjecture, and it agrees in all cases. Otherwise, we would have discarded it, of course. And so now we can, again, we write down a general. So in a sense, we're looking at the general loop momentum numerator twice. The first time we converted to Feynman parameters just to find out the set of lattice points that we even want to worry about, because there's a huge number that can never arise. And then the second time around, we put in general coefficients, again, just as in the analytic approach, to each term. And we convert to Feynman parameters, and now we look at everything that's not in the relative interior and require those coefficients to be 0. In fact, we require those coefficients to be 0 order by order in D, because we don't want our original numerator polynomials to have D-dependent coefficients. That's, at least from the point of view of study of evanescent objects, that would be kind of defeating the purpose. And it turns out that here you find 3. And if you remember, well, actually, I didn't show you the analytic results here, but there are actually only 2 that come out of the analytic approach. So you might wonder what's going on, but hold your curiosity for just a couple minutes. So we have 2 approaches, and so of course the first thing you want to ask is, do they agree? And the answer is yes, but the comparison's a little bit subtle. And the subtlety arises from a number of different sources. First of all, the geometric approach it cares about convergence. It doesn't care about how you determined UV convergence. So it actually only imposes weak UV convergence. In fact, there's subclasses of weak UV convergence too. It's what we call simply weakly UV convergent, namely that there is, by power counting, a potential UV divergence, but its coefficient vanishes exactly because of kinematic reasons. So for example, it might be proportional to K1 squared. And when you have a massless, when K1 is massless, then it vanishes. So these are picked up by the geometric approach. You need to impose that as an additional condition to compare with what came out of the analytic approach, or conversely, you have to relax to the right kind of UV convergence criterion in the analytic approach. In addition, there are non-trivial numerators you can write down in loop momentum that vanish identically in the parametric space. And these things are special kinds of total derivatives. And so you have to account for those things. And that's actually the explanation of the discrepancy in counting at one loop. And in general, you can have general total derivatives that are not locally finite, but still get scooped up by the polytopes, and you have to take those into account as well. And when you do that, and we've compared a bunch of integrals, the analyses for a bunch of integrals, both the planar and non-planar double box, what we call the Beetle integral, which is essentially a triangle and pentagon, two loops, again, a 4-point integral, and also the 3-loop ladder. And after an appropriate analysis of the total derivatives and the differences in UV convergence, then in fact we find that we reproduce the results of the analytic form. So that's support for the conjectures and also for this way of thinking about things. Now, I realize I'm running a little bit, I'm probably in minus territory now, am I, or no? Okay, so, and I wasn't paying attention when I started. Okay, all right, so, this is now actually more work in progress, and one of the ways that's actually now in a package by Yang and his collaborators called Neat IBP is the traditional IBP approaches. They generate a huge system of equations, and then you have to solve that system of equations. And a lot of the information in those equations is redundant because you simply hit everything with derivatives by brute force. And so one of the things you do is that you double propagators. And generally speaking, most of the integrals you're interested in, you don't have double propagators. So you can use them, you can avoid introducing these double propagators using what I call generating vectors, and this has become known as the syzygy method. And so the basic idea is that instead of just putting in every possible vector here when you're constructing total derivatives, you choose the vectors in such a way that if you contract it with the derivative of any denominator, you get something proportional to that denominator. And so any term that would have a squared denominator, a doubled propagator, automatically gets it canceled out. It's reduced back to a single power. And this is, in fact, something where you're looking for syzygies. And so it's precisely an application of computational algebraic geometry and Grosvenor bases, and a little bit more technology than what I showed you earlier in the talk. And so here, the question is, if you'd like to know, can you find IBP relations that are strictly within the set of finite integrals? And so, of course, you could generate all possible total derivatives and try and find linear combinations, et cetera, but one can also generalize the syzygy method. Now you have an additional numerator, and in addition to having this requirement on the denominators, then you also require that the generating vectors contract with derivatives of numerators to produce something which is back in the same class. And that's actually work that is going on currently with Yang and his students, and I guess also former student. Yes, so that's one other kind of complement to the thing. So, as I mentioned earlier, the original at the very beginning, the original motivation is to try and look for a simpler representation of amplitudes. And okay, we're just at the very start. We've only classified finite integrals, so we can't really hope to organize the divergent parts of amplitudes. But one thing that's interesting, if we look, for example, at the two-loop 4-point all-plus amplitude. So this is a very special amplitude because at tree level, it vanishes. At one loop, it's then finite. And so at two loops, generically, an amplitude would have a 1 over epsilon to the fourth leading singularity. This one only has a 1 over epsilon squared. And in the standard representation, which I haven't shown you here, but contains a few more integrals, then of course there's a lot of integrals here which are 1 over epsilon to the fourth. And so, and the way that the 1 over epsilon to the fourth disappears is by cancellations between integrals. And as we know, implicit cancellations are not a good thing. If you want a simple form, all the cancellations should be manifest. So if we convert the double boxes to these finite numerators, then one of the interesting things that happens right away is that you get an explicit factor of epsilon out front in this representation. So so this is already manifestly only 1 over epsilon cubed rather than 1 over epsilon to the fourth. And moreover, because you have an epsilon in front of finite integrals, then you get to cross out some of these integrals directly. And so in that sense, you have fewer integrals and fewer coefficients. And I don't actually have a slide for it, but it turns out that some of these coefficients are also at least in a qualitative sense, simpler than the ones that you see in the more traditional representation. It's if you want to count the number of characters that you need or the number of lines in Mathematica or something like that, then that's a way of characterizing it. So that's at least a sense that there's some of the motivation is justified continuing on this program. So another thing you can do is you now have access to a different way of getting analytic results for some of these complicated integrals. So of course, the differential equations method is kind of the standard, and maybe everything can just be done that way. But I think it's always nice to have another tool to think about things. And so one of the tools that was developed a few years ago and maybe didn't become as popular as it could have is partially because it's written in Maple, which is a very minority language in the community, although I have two good collaborators that swear by it. So there's a tool that was developed by Eric Panzer, which for linearizable, where the denominators can be linearized in a certain sense, then it can systematically evaluate these integrals in terms of hyperlogs, which are a class of Goncharov polylogs. And so here we have the opportunity to apply this to a very non-trivial integral. So we looked at some of the, or at a couple of the rank 2 finite pentaboxes. And it turns out that all integrations but one are linear, and that's not so surprising because the alphabet, the symbol alphabet for this integral has a square root of a certain determinant. It so happens this appears relatively late in the game, and it appears in a form where you can simply do the partial fractioning by hand. You get a certain Feynman parameter squared minus the determinant, and so of course you can just do the partial fractioning by hand, and that's also something that we're playing. So somehow the spirit and amplitudes from where I stole this concluding transparency was to use ChatGPT to generate haikus and other bits of doggerel. But my own experiments with ChatGPT were yielded terrible results to my taste. So I did one by hand. I've given you basically a picture of two approaches to generating finite Feynman integrals. And I should say that the Landau approach can be then applied systematically also to find the independent set of 1 over epsilon integrals, 1 over epsilon squared, and so on and so forth. It's something you can develop that machinery. It's a little bit less obvious how to do that in the geometric approach, but it's something that I'm thinking about on some occasions during my morning shower. And here it's something where we have Newton polytopes plus the Birkesh-Forsgaard-Passer theorem. And I think here it would be interesting to explore a little bit more the connections to tropical geometry that also might simplify some of the analysis. And then I think that there'll be some interesting applications in the future, both to amplitude structure and to generating analytic results from integrals. Thank you.
Thank you, David. I've been asked to make sure the questions are recorded by passing the microphone around. Who would like to go first?
I have a question about the geometric approach. It's a conjecture at about 22 or 23 page. Could you move to 22 or 23 page?
Okay, let me go back here. Why don't you just stop me when we get to the right transparency? This one?
Yes, 23. This conjecture, to what scale has it been verified?
So I'm not exactly sure what you mean by the question of scale, but so far we've looked at a collection of integrals. We've looked at the planar double box, the non-planar double box, which in spite of the fact that it doesn't manifestly satisfy the requirements of the BFP theorem, you can actually show, and actually Anon knows this very well, you can show that it does. And an integral which we call the beetle, which is this object. So it's kind of like a triangle, a triangle pentagon, and also the 3-loop ladder. And we've looked at this essentially for all the ranks, all the degrees of loop momentum polynomials in the planar and non-planar double box and in the beetle, and up to degree 4 in the 3-loop ladder.
Thank you.
No, I'm not hiding anything. It's still a conjecture, but there's a fair amount of evidence that, and that they're also, let's say, we have some hand-waving arguments why you might believe the conjecture, which I haven't discussed, and we're still kind of thrashing out. But yeah, it would be nice to prove both of the conjectures that this relies on.
So yeah, thank you, David. I had some discussion about this with Leonardo as well, and one thing that came up is the conditions in this theorem that you are based on are somehow too strict for what you want. But we are actually familiar with situations where the conditions were, are a bit too strict. For example, for the application of expansion by regions, there's a similar situation where if all the monomials are the same sign, then it's clear that there would be only endpoint divergences and then everything works. But so basically only facets provide the regions, whereas in reality, this is used in Minkowski space where that's not the case. I'm wondering what the conjecture is about the conditions under which this would work. So I think it is quite clear that if there is a Landau singularity in the interior, then this would not work. Because I mean, then you can just take that point in the interior and that would lead to divergence. So perhaps, I mean, I want to ask whether you have evidence that supports this. So long as there is no Landau singularity, then even if f has negative sign, even if the signs change, then it still holds that the points in the interiors would lead to a finite integral.
Yeah. So in a certain sense, the non-planar double box is precisely an example of that. That at least in the standard representation, it's the f polynomial is not manifestly of uniform sign. Now, you can rewrite it in such a way that, well, I don't know about rewriting the f polynomial. You can rewrite the Landau equations so that they correspond to something where there's manifestly no singularity in the interior, and there are other integrals where you cannot do that. So we haven't looked at these more complicated integrals where there's manifestly a singularity in the interior, but the conjecture there would be that you can find a remapping in some sense to turn to turn the parameter space inside out, and so that in this turned out version, you now have facets that correspond to the interior singularities, and then you apply, in a sense, you apply the BFP theorem to the original set of variables and also to the inverted set of variables. So yes, the conditions on the BFP theorem are in a sense too strong. However, we don't have any example of something where the key element, the issue of the relative interior, is violated, and still there's a finite integral. And also everything that is in the relative interior does seem to be finite. So that actually does seem to match very closely. Now, so there one has to be a little bit careful about what you mean by finite integrals, because there's also classes of finite integrals that are what we call evanescently finite. So where they're finite, but they're not really doable in 4 dimensions, and the finiteness comes from a cancellation of epsilon over epsilon. Those things are not, at least to our present understanding, detectable in the geometric approach, and they would, in a sense, live outside the relative interior.
Sorry, do you have an example of what you mean by the turning out map?
No, this is
just an idea that
this is an idea that
how you could manipulate the
yes,
integral, so you could,
yes.
yeah, okay, great.
I comment how this maybe if
go ahead.
It's okay. So there is so on Friday I'll discuss this. There is an idea of how to dissect a polytope and create instead of one, several of them, but in such a way that the singularities that in the one that comes out of the Newton of the original semantic polynomials the singularity is inside, then you dissect it in such a way that all the singularities would be on some facets, on some faces, but in this case, facets are important. So now what David said sounds.
So that the singularities lie at the top mentioned facets of each.
Yes. In each of the ones that the daughter wants. So now I think what David suggested, if I understand correctly, is that if you look at the interior of each of these and you select points that lie within as
Yes.
your numerators, then is this what you
Yes.
mean?
Yes.
Yeah, then it might.
So, I mean, I'm very ignorant of the mathematical literature on this, which I'm sure is, people may have studied this question already, but but at least there's at least a large class of integrals where you can show that the theorem gives you, where you can argue that the theorem gives you everything. And so as I say, relying on a certain number of conjectures, right? So it's nothing is completely proven.